Right. I'd like to thank the organizers for such a nice meeting, so many interesting topics and people. And I'd also like to thank the audience who stayed this long, even though I'm not going to speak about ordinals. And I'll speak about a paper that has just appeared a few months ago. And co-authors Sonia Moran, Elaine Pimentel, and Marco Volpe. And I'd like to thank Elaine and Sonia for having written the bulk of the slides you'll see next. And there will be references in the, I won't stop to cite who the references are. They're all at the last of the slides, and if you really need them now, this is on my webpage already. So a view from 30,000 feet, taking a high-level look at things. So we'll go back. Jensen in 1935 came up with a sequent calculus. It was a nice thing for doing this cut elimination theorem and proving consistency of arithmetic and first-order logic. But some of us have tried to use it in theorem, in specifying things in computational logic and computer science, and it's really quite awful for that in many ways. It's very chaotic, and lots of things slip around. I mean, there's not much structure there, and it's really like due to these rule permutations. So many people, in fact, don't use it as a representation, a system for doing proofs theory. However, a couple decades ago, we have Jean-Yves Girard and Jean-Marc Andreoli, and there's this introduction of linear logic and the notion of polarity. Is everything okay?
It's recording. You're talking, you don't have a microphone. Oh. That's good.
Okay, thank you. Right. So they introduced the notion of polarity, and there was a concept of a focused proof system, and it was first applied to linear logic. And what you learned in the linear logic setting is that you could use this focusing concept to build large-scale rules, not the micro rules that were given by, let's say, Gensen, small introduction rules, structural rules, but you could build things that's much, much larger in a sense, okay? But that was largely done in the area of linear logic. So what I'm going to do today is apply these notions here to intuitionistic logic and classical logic and use it to describe essentially a mechanical way, if you will, to build synthetic rules from axioms. Okay, so that's the overview of the talk. So this concept goes back a long time. How do you take axioms and make inference systems out of it? And can you do it in arbitrary formulas? So there are lots of nice examples like this one taken from sort of a work in geometry. So if A is a point in a line and A is another point in another line, okay, and so on, you can read that. Then you either have the same point or the same line. And how would you make that into an inference rule? If you don't like logical connectors like imply and and, you could write it as an inference rule like this. If you have these sequence on the above here, there are sequence, you could put this sequence at the bottom. Okay, so that's a form. That's one way to do it. There is another way to do it, and it's this one, where if you already have these as an assumption and you read backwards, all you need to do is try to show, you can add either A equals B in one case or M equals L in the other case, okay? So there's multiple ways to do this. So a good theory of this should explain both of these approaches, for example. And you can imagine doing this in many other areas. So here's a notion of a way of axiomatizing geometry with the notion of congruence. I won't go into the details, but you see they're very simple horn clauses. You can get one of two different kinds of axiom rules, inference rules for them, or you can take the second one there and you can get two different forms of this one or this one. You could choose just one of these and still remain complete. Okay, so this is, like I say, an old problem, and how can we use this notion of polarity and focusing to simplify it? Okay, so usually what we have, I mean, in a very high level way, you have first order logic and it's represented by a sequence theory system. However, you want to work in a mathematical theory, not necessarily a logic, so you have all these other axioms that you'd like to do. So how do you build them in to a proof system? Well, this is a problem that's been looked at by many. Okay, Sarah is here, for example. She's worked on this for many years, some years ago. There's other approaches that others have looked at in the area of modal logic and substructural logic. And if you're willing to add equality theories, then there's a lot of work by Gilles Dalwick and his team on also another style of answering this question. One approach is just to say we have non-logical axioms. So let's just say we know that P implies Q. That's something we want to assume. And we also know P. So obviously we should get Q as a conclusion. And you can build that if you just say, well, these are just axioms. When we get to that part of a proof, we can just say we're done. Of course, that doesn't satisfy the Hauptsatz, cut elimination in general. A slight variation of that is to assume sort of these kinds of sequence, if you will, okay, not just formulas, but sequence. But basically, you have the same problem with the Hauptsatz. Cut elimination doesn't hold directly. However, one approach that sort of does work is to represent them as non-logical rules. So we have logical rules for the introduction and elimination of connectives, if you will, left introduction, right introduction. Or we could just say, well, when you run into let's say the propositional letter P and rating bottom up, I can put in the Q. Or, and in the other axiom, I could just say I can add P at any time as a hypothesis. So that would be an approach to work. But, and we now have a cut-free proof of P implies, of Q from these two rules. So that can work. So now the real question is, how often can I do that kind of project? And so that's what bipoles and focusing will do for us in a minute. The goal is, of course, to have synthetic rules. And in this talk, I will mean until the very last slide, synthetic rules are rules that mention only atomic formulas. There might be atomic formulas below the line, above the line in multiple sequence, but there's no logical connectives implied. Okay. One of the goals would be to say have a completely logic-free and only inference system for some weak theories. Okay, right, so this is what I mentioned in the very beginning. We'll classify formulas, axioms in particular, the ones up here, as being part of a hierarchy of polarities. And then we'll use this notion of focusing to polarize some of those. To turn some of those polarized axioms into inference rules. This approach I'll be presenting is systematic in the sense that it's actually computational. And in the published paper, we even have a program that shows how to build synthetic rules from axioms. It's uniform in the sense that at least it works for first order and classical logic, the same method. It generalizes things that are already in the literature. And we get cut elimination guaranteed for the synthetic rules we add. Okay, so you do it, you follow this framework and you get cut elimination for free. Okay, so here's the highlight, the rest of the outline. I'll talk about sequent calculus, but I assume everyone here knows it, so I just pick a few high-level points. If you think more about natural deduction style arguments, you're reasoning down from assumptions to B. A sequent is a rearrangement like this, of course. We call the left-hand side a context. The rules will be divided into, let's say, right introduction rules and left introduction rules, and these are typical examples. Okay. We end with initial rule, not an axiom. I won't use the word. I'll use axiom for non-logical things that I might want to assume. Initial is for that one inference figure here. And there's the cut rule that if I read backwards, all of a sudden I have a formula that might have required some invention, a lemma, let's say. It's not necessarily a subformula of anything in the conclusion. So from the point of view of proof search, there's a step of invention. All right. So at least for the automation of logic and for many other reasons, we like to avoid the cut, even though it can cause an explosion in proof. But nonetheless, it's an important rule that we'll be avoiding here. As a result, we'll say that cut elimination gives us a subformula property, which is another way of talking about analyticity of proof. So I'm sure everyone is familiar with that. And the sequent calculus, as I mentioned earlier, has been used in many different applications, but still it has its faults. So let's keep moving. Now, polarities and polarized formulas. So what do I mean by that? So in the sequent calculus, let's just say I have A, B, A0, A1, and B. They're just atomic formulas, say first order logic, if you will. And I have this sequent. Now I have one formula on the right, B. I have a little tiny implication, right? These are just propositional letters. And gamma could be 1,000 formulas. Why not, right? We're doing logic programming or databases, and there's just lots of things in my program or database. So in a setting like this, there's an enormous number of things you could do. Probably everything in gamma has an implication or a universal quantifier in front of it, right? And I could introduce any of those. But I could introduce this, and well, maybe B is an atomic formula, so not that. So the implication left rule, if I choose to do the implication left rule, there are two protocols I can apply, which will make the proof much shorter, let's say, and I don't lose completeness. One protocol in this particular setting is to say, okay, this is implication introduction right now, but I want the right premise here to be trivial. In other words, it needs to be the initial rule. Okay, and I can just always impose it if I have an implication between two atomic formulas, if you will. And I never lose completeness. And I'll call that the negative protocol for obscure reasons. Right now, the letter T is often associated for the head of this. The tet is trivial. In this case, the A0 must be B, right? If that's initial, and it wasn't initial before, A0 must be B. And this is called backchaining. There's a chaining of implications. So remember, I could have 1,000 formulas here. Once I choose to do implication left here and split, I could go back and do something here. But this will be called part of the focusing. If I pick this formula to develop, I'll keep on all its subformulas until I get to the very end, at which point I want this premise, like here, to be trivial. That's a slight generalization of the picture up there. So it essentially says, in order to prove A0, which is what B is now, A0, find the rule that implies ultimately A0 and prove all the sub-goals, if you will. That's often called backchaining or prologue, if you're familiar with logic programming. There's another protocol, it's often called the positive protocol, and the tail here is made trivial. In other words, the right could be now a more substantial proof, but I'm going to ask for this one to be trivial. And that also works. You get completeness if you make such restrictions. All right, so in that case, the context here must already contain the A1. So it already sits here, and I can only fire this implication if its premise is sitting there already ready to be used, if you will, okay? So this is an example of forward chaining. So if I do the same sort of entailment here, I could, let's say I will only use this implication if every one of these A's is already sitting in the context. Okay? So that's the nature of this protocol. So these are all trivial proofs here, right? They're just checking that they're in there. It's not a proof, it's just the initial rule. Whereas here, I could have very substantial proofs, okay? And then what I continue with is, now that I have A1 through A4 in my context, and I have this rule, I can add A0 to it and continue. So here I have A1 through A4 plus A0, and I continue making the proof here. And that's forward chaining or data log in some communities. Okay. And yes, you can, of course, make them mixed if you want. You can make some things negative and some things positive, and still you don't lose completeness. So just a more concrete example. Here's how you specify the Fibonacci series as a binary relation. So fib of n, capital N, is true if the second argument is the nth Fibonacci of the first argument. And if I look at how proofs go in this setting, how do I prove? If I have this, let's see. Yeah, this is a negative protocol. So in order to prove this, actually that's not the right, Let's just say this slide isn't quite accurate what I have here, because what I have here should be an instance of one of these formulas. But the idea is correct, that in order to prove that the fourth Fibonacci has a value, you have to compute the third, and the third requires the 1 and 2, and the 2 requires 2 and 1. And it turns out that you get, these are trivial, but you get a proof here and then you get a proof here that's bigger. And if you increase this, it keeps redoing and computing. So this, in fact, this protocol gives me a unique proof, but it'll be exponential in size. All right, I mean, it's a proof, but it's just big. If, however, we do it in bottom-up protocol, we get the fact that when we make these inferences, we'll have to generate the 0 first, and then the 1, and then the 2 gets inserted by running this forward, then the 3 gets inserted, and so on. And you might get lots of proofs, but the shortest one, it will be linear in size. Okay, so this is just a well-known choice between backwards chaining and forward chaining in, let's say, proof search, known long ago in AI literature, for example, or automated deduction. So what's the more general picture? So that's the spirit of it. So let's take a standard first-order logic. In classical logic, I'm going to have pluses and minuses attached to the classical connectives, these ones, and they will essentially be part of the polarization. Earlier, polarization was limited to atoms. Now anything built with a negative or and will be a negative formula at the top. It can have positive subformulas, but the top, if it's a negative and or a negative or, will be itself a negative formula, okay? And dually for the positives. And I have first order quantifiers, and the universal will always be negative, and the existential always exponential. But the conjunction and disjunction, for example, are ambiguous. We'll resolve that in a second. And in intuitionistic logic, it's the same as classical, except you don't have the negative or and the negative false, its unit. You only have the positive. You have an or, but it's only the positive one in its unit. And you add an implication, and that will be negative, just like the universal quantifier is negative. It's just always negative. Okay. So there's the original language, and then you build things with these fancy symbols in it, and you get a polarized formula. Now, how do you move to polarized? Well, you arbitrarily, or at least at a large extent arbitrarily, label the atomic formula as either positive or negative. You're free to make those choices. Sometimes we make them all positive, sometimes all negative, but you can mix. And when you're doing this let's see. So true and conjunction have to be labeled with either a plus or a minus in the polarized formulas. And if you're in classical logic, you also have to resolve which or do you mean, the positive or the negative. If you're in the, okay. And if you have a lot of occurrences of these, ands and ors, you'll have, if you have n occurrences, say, you have 2 to the n ways to do that. So there's just a lot of possibilities for polarization. If, however, you're in the intuitionistic setting, then you would just do this. There is no ambiguity about what the or and false should be. And now again, a formula is positive if it's a positive atom or its top level only symbol is positive, and similarly for negative. Okay? So here's a hierarchy, and it's kind of the obvious one now. We'll say, independent of how the atoms are polarized, we'll say N0 and P0 are the same and they consist of all atoms, positive or negative. But then we'll start building up formulas so that the next level of negative formulas are built, n plus 1 are built from positive ones of the lower fragment, or you take negatives of the fragment you're in. Okay, so you're stratified like this. I'll give some pictures in a moment. But you get a rather familiar sort of hierarchy formed. Okay? You're familiar with this from the arithmetic hierarchy, of course. So another way to view this is if here's a formula where there's a positive, but there's also some more positive formulas. So we group them together as there's some positive, and then there's some negative underneath, if you will. Okay. Or we could do this a similar thing with a bunch of negatives grouped together and then positives. So we'll view that as sort of one, if you will, one big connective in the future. And so it's a negative above a bunch of positives. And you can do this uniformly in intuitionistic and classical logic. The only real difference at this part is there's less ambiguity in intuitionistic logic. There's more in the classical setting. All right. And if you stick to the class 2 here and 2 here, those formulas we'll call bipolar formulas. And it's really the limit as far as we'll go. Okay, bipolars. So the answer will be, what's a synthetic rule? It's choosing a bipolar formula. Okay, and we've mentioned this already. So here's an unpolarized formula. So there's the question is, how can you polarize this? Well, you could do this. Once it's polarized, this is negative, and that can be positive or negative. And that's a classical bipole if we're assuming P and Q themselves are positive. So we have negatives and positives. Whereas here, there's no way to make this a bipole in the intuitionistic setting. Okay. Focusing in bipoles. So if we again return to implications of this form, we get, this is like, okay, I used the word focus before. So the notion is that we commit to repeated implication left. So if I start, I must keep going to the right. Okay, and depending on the polarization here and here, this is common on no matter how I polarize the atoms. But now either that's initial and these are not, or these are initial and that's not. Especially when you make a monolithic change, a setting for the atoms. Okay, so the point, the important aspect of focusing is that if you make these really strong restrictions that once you commit, you stick with it, okay, and there are proof systems that describe it. I won't illustrate them directly, incomplete. But the idea is kind of clear. Once you start, you continue. And when you end, you have this question of, well, how have I polarized? Do I stop with an initial or do I continue with the proof at that point? So here's an example of an unfocused proof, and we're using orange for negatives, and I guess here the blues are positives. And I can just reorganize that into some focus proof here. So if I see I have a negative here and negative here, but I could have done them all together. And then there's positives and positives. So this kind of building of proofs in a very rigid fashion under this focus discipline is completely complete. Okay, so I'll show a little bit of the setting here. So there's focus versions of LJ, again since LJ and LK. You add the F, you get the focus versions. It's something I worked with Chuck Liang some years ago. And we have these things called down arrow sequence and up arrow sequence. They're like this. So in other words, the formula between the down arrow and the turnstile here, and the down arrow and the turnstile here, this is the focus, the one place that you're going to do introduction rules. If there's a down arrow, the only place among the thousands of formulas you might have that you can do an introduction rule is in the focus. Okay? And the other rules are with the up arrows. And again, the only place we'll do any introduction rules are between the up arrows and the turnstile. So here I can do right introduction, here I can do left introduction. So there's a nice regiment for rules like this. So here, if I have an implication here, there's a focus on that, so I must continue the focus here, and I continue the focus here. That's the spirit of it. And over here is in the up arrow phase, and I move this to the left side. So here, there are multiple formulas in this zone, if you will. Here, there's always exactly one formula. Okay. Now, one of the keys that I haven't really mentioned here is that the negative and invertible go hand in hand. If you have an inference rule that's invertible on the left, we call it, it's introducing a negative connective. If it's invertible on the, sorry, it's on the right. If it's invertible on the left, then it's a positive connective, okay? All right, let's continue. So, so if you're in a phase like this, and there's no formulas that are invertible anymore. So imagine you're doing proof search and someone says, well, you can always do an implication right rule. So you just do it, you don't think. You can always do a case analysis. There's possibly many ors on the left, so you just do all the case analysis at once without thinking, right? So that's invertibility. And invertibility means that if you do it, you never lose provability. So the negative phase, or this up arrow phase, is intended to be exactly that kind of phase. If you, in that phase, and you encounter now a formula like or on the right, positive or on the right, you go, oh, this is not something I can do mindlessly. I need to make a real choice. So what happens in that kind of setting is that the formula will be moved to the outside. In other words, moved to this out of that zone into this area. I'll show you that in a second. And we'll come back to that at some other point. So this phase is just a matter of, let's just get rid of everything that's simple. And if it's not simple, we move it out of the inner zone, and we'll come back to that. So if everything has been moved out, in other words, that zone is empty, and I always read proofs going bottom up, then I can continue, this is an intuitionistic logic, by taking either a negative formula, which is on the left, and putting it in this zone, and now I can do left introduction rules there, or I have a positive formula on the right, and I do a focus on it. And notice, this will be the only time in this calculus where I do a contraction. There's n once below the line and now twice above. So the decision to say, I want to work on this formula or focus on this formula is exactly the same as I want to make a copy of that formula. It's not independent now. Okay, so yes, change arrows. So if, however, I'm in this phase and the down arrow phase, and I see that, oh, that's something in this phase and this phase, that's something that is in fact invertible, then I give up and I say, I enter this other up arrow phase, and I say, okay, I now go into my invertible phase. Okay, so these rules are called release. I release on my focus because what's coming next is not a difficult choice, it's a mechanical choice, right? You can imagine in the positive phase, I'm speaking to some oracle. What should I do next? You know, what instance of a quantifier on the left should I make? Or which choice of an or on the right should I make? That's the positive phase. The negative phase says, I'm not speaking to anyone. I know exactly what I do. Okay? So in this case, the system realizes, oh, this is the easy job. I switch to this mode where I do the easy things. And derivations end at this kind of point where if I'm focused on a negative atom, then I'm able to quit. And if I'm focused on a positive atom on the right, I'm able to quit. But notice if I'm focused on a positive here, I have to do this rule, release. I have to do this rule. Even if that's an atom, and even if it happens to be there, I must do the release. Okay, so it's a very disciplined calculus in that sense. So as I was mentioning, once the focus is released, you do these invertible rules in a very eager fashion until you're done. And then at that point, anything that's not easy to do, I move it into storage. That's what we say here. We move this P, which is not invertible in this situation, into storage outside. And here I take a negative, no, I have that P should be an N, and that N should be a P, sorry. So we're storing the things that don't belong in that phase because it takes some real work. All right. So we now organize sequence systems into up and down phases entirely. And a synthetic rule is actually the result of looking only at the border sequence. So a border is now something which is up arrow, and there's nothing to be dealt with. So the only way to prove a border sequence now is to make a decide. Okay? So at that point, the character of what comes next is decided, is determined from that choice. So proofs look a lot like the following. And this works again, like I say, in classical and intuitionistic logic. And we'll speak about a bipole now. So there's a positive phase, which is this reddish color here, down arrow phase. And the blue is all actually one phase, but we're marking it as, in this phase, I'm making some hard decisions, if you will. So the plus on the right is determined in this phase. The upper arrow phase is just invertibility. So we just, the meaning of sequence doesn't change as I go up here. And finally at the top, I'll be moving atoms, things from the center into storage, if you will. And when I'm in the bipole setting, in other words, restricted to the order of nesting of at most 2, then the only things I'll be storing will be atoms. Okay, so that's getting back to the fact that synthetic rules are really about atomic formulas only. And in that case, we start with a border sequent here and a distinguished formula B, and I decide on it. Then I make choices, I make invertible rules, I store whatever atoms are left, and I'm now back to possibly several border sequence. And that's the definition of a synthetic rule. Just drop the up and down arrows, and that's my synthetic rule. And that works for the classical and intuitionistic setting. Okay? So you make a choice on a formula, you make your choice of moving through the formula if there are choices. Then you do this invertible thing, which in some ways doesn't change anything, it just reorganizes the formula into sequence. And then I'm left with border sequence. So this is why they're called borders. Okay, so let's just do some examples here. One thing that's easy to notice is if B is a bipolar, that means it's in the second part of the hierarchy, then any synthetic rule for that is a bipole, which means as I move through, the only things I finish after one phase, these positive, negative phase, and the only thing I'm putting in storage are atoms. And every synthetic rule is, and if every synthetic rule for a given formula is a bipole, then it's in fact a bipolar formula. It's just showing that they're the same concepts. And again, it's systematic enough that you could take a language like lambda prolog, which is a nice meta-logical system. Partly it's a nice, and you can compute these inference systems, and I'll show an example in a few minutes. And one of the reasons it's quite nice is because that language has an unproblematic treatment of unification and eigenvariables at the same time. Okay, because we're usually treatments of synthetic rules don't have quantifiers in because, well, the bindings get confusing and tricky. That's all sort of essentially solved and quite easy in a language like this lambda prolog. Okay, so it's mechanizable easily enough. So a little bit more on the meta theory then. Let's take a theory, T, okay, and and then we assume we know how we want to polarize things. Then we take LK and we make an extension, or LJ, we make an extension. So what are we doing? We're taking those base state logics and adding the synthetic rules that correspond to the formulas in T. Okay, so there's, in the background, there's an implicit notion of how we want to polarize atoms and formulas. We get then all the axioms here, bipolar formulas as axioms, generate inference rules. So now add those inference rules to either LK or LJ, and you'll get a new system. And in fact, that new system will enjoy cut elimination. And it's fairly easy to prove it, okay? Because we have a general cut elimination theorem for focus calculi in general, it just inherits at this point. All right, so let's just do a few examples. So we start off with an unpolarized axiom. There's many ways to polarize it. Let's take a few. There's a few. So again, orange means negative, green means positive. And so there's not so many choices, but here I have a plus that's green, an and that's green, or an or that's here orange. So that's the difference. And this Q is sometimes positive, sometimes negative. And the question is bipolar? Well, that formula is a bipole. It's just a matter of parsing it correctly. If you do the calculation of what that means, in other words, how do you do this? You put that formula in this particular zone. You do all the introduction rules that you can on the left and follow this discipline. And sometimes you'll have a release, and then you do the asynchronous phase. So first you do this a positive phase followed by a negative phase in all these cases. You end up with a top-level sequence of this kind. And so what you observe is that, for example, here I stored some atoms. There's a border there. Here I know that this must be initial, so the QT must be present in gamma right now, okay? And so if I write that as a synthetic rule, I know that gamma must be written as gamma prime with this QT in it. And the inference rule looks like this. So, I mean, at the bottom, I know I need a QT on the left. And at the top, I know I add this to the left, that to the right, and the other premise, I add that to the left. So it's a rule just with atoms, okay? And this calculation helps you compute that. We can look at another example. So you could take the one in the middle. This time, it's still a bipole. You do another calculation, you get another synthetic rule, okay? So you can continue this. There's many choices that you can make systematically. And we can even go back and say, look at this one, but that's not a bipole. So we just give up. There's something you can do beyond bipoles if you want, I suspect. I'll mention it later. But let's just say for this project right now, we just say, oh, that's not a good, we can't make an inference rule out of that. And so one formula, this one, can give rise to this or this synthetic rule. And you can make a choice of one and stay complete. In other words, instead of having that as an axiom, you could have one of these as an inference rule. Okay? So let's just do some more examples quickly. So here's a geometric implication. Let's see, Q is a conjunction of atoms. The P's are atoms themselves. So the only real choice is what polarity should the atoms have, and what this conjunction here, here, and here, this disjunctions, what polarity should they be? So it depends. If we're in classical or intuitionistic logic, then there's only one choice for the ors. But there are two choices for the ands here and here, okay? It doesn't need to be a uniform choice between them, but let's just take a look at what's typically done. So one choice is to polarize, let's see, yeah. So if we polarize all this as positive, those atoms positively, and the conjunction positive, and here it doesn't seem to matter which of those I choose. I mean, I have to choose one, but if I choose one or the other, I get the same effect. Here I get an inference rule that says, well, the P's must be present here, and if that's the case, I can add the Q's here in that premise and these other Q's in this premise. Okay, so that's one reading of that as an inference rule. But there is and in intuitionistic logic, I have yet another, and if I get rid of the up and down arrows, this is what it looks like. Okay, so this rule is known in the literature, for example. Another choice would be to polarize the atoms negatively. In this case, the choice of conjunction doesn't matter, and also here. And I get a rule that looks much more like this. I don't have any requirement what's down here, but I put Q's in some of the premises and P's on the left and P's on the right on other premises. Okay. It's another form of the inference rule. If I continue with this, so in this case, this example has a negative or, so this would only make sense in the classical setting. I get inference rules that look like this. I have the P's, all must be present on the right, so there's a lot of possible atomic formulas on the right. And if that's the case, then I add the Q's this way on the right as well. Okay. Again, most of these are known in the literature. I guess I could show that, but okay, it's the same kind of choices. So you run into a lot of these choices. And finally, you can make choices here. Yes, so in the case that you make them all positive here and the or is positive, you get simple rules that look like this, quite natural, where the bar, of course, means that all the atoms are present here. So if I have a very simple axiom like I started to talk out with, this is generated, we used uni with a P to denote that there's positive polarity for the atoms in this case. And if I make this choice of polarities, I get another well-known choice. So here I'm generating the negative version of the same axiom scheme. Okay? And finally, horn clauses, just do one more example. And this is rather simple. This is just called forward chaining. If I am choosing positive polarities here and positive for the atoms, and I get, if everything is chosen negatively, then I get back chaining as a familiar form of inference rule. Okay, and just for a matter of, so here's some programming, right? So if you have an axiom like this, that if U is adjacent to V and there's a path from V to W, then there's a path from U to V. This is W. This is the obvious transitive closure of the adjacency predicate. You can type it, you can code it almost exactly as you might expect in a language like this. This represents the binder in lambda prolog. So there's 3 binders for the 3 quantifiers and so on. You ask a query and it'll print out a goal of this form. Okay. In the background, we already had to make an assignment of polarity to the atoms. Okay, so I could show you several examples of doing that. Well, so just this is the bottom-up version. So in the background, I said that these had to be positive, whereas if I say they're negative in the background, then I get this is computed for me. And you can even run it on examples like this. So U is a subset of V if everything in U is in V. Okay, there's various ways that could be run as well, positively and negatively. And just some more examples of this kind. So people do this in geometry a lot. Yes, so you can take these clauses, in which case all these are horn clauses, and you have your choice, but you can get inference rules such as this. Okay, and just a quick note, what happens if you go beyond bipoles? So a nice example of this is to take the Gödel-Dummett logic. This is essentially intuitionistic logic plus this linearity axiom, linearity in the sense of Kripke frames. And then that's an axiom, so you want to have that on the left. Things that are stored on the left have to be negative, so somehow we have to make that formula negative, but I can't, but the or in intuitionistic logic must be positive. So I must do some trick like this, put it under a conjunction. Right? So polarity can easily be broken. You just wrap it in something, and true. And if that and happens to be positive, then that formula is positive no matter what you wrap it in. And similarly, if it's negative. So this formula is negative on the outside, positive, then negative again. So this is not a bipole. It goes down too many levels. But you could imagine you run this focusing mechanism. You're focusing, it's perfectly fine. And then what gets stored and moved out is this is not an atom, right? This is an implication. So the full calculus doesn't mind. You can move out, you can do this not just on atoms here. And so in both cases, what you've moved out is that. So you get a bipole, you get an inference rule that looks a little bit like this. How do you prove gamma entails C? Well, you can start up 2 proofs. You have to do it conjunctively, but in one, you're allowed to assume P implies Q, and the other one, Q implies P. Okay? Now, exactly what does that mean? Well, it depends a bit on the polarity. If it's positive or negative, it means you have a rule that says, okay, you either have P on the left and you can add Q, or in order to prove Q, you have to prove P. It's exactly the sort of things we've looked at already. And my guess is this resembles something like hypersequence in my thinking. It resembles a little bit a rule like this, that if I have a bunch of, so for those who don't know, it's okay, it's just, I have a bunch of sequence lumped together here, and this is a kind of communication rule that people have looked at in the context of hypersequence. So one of the best proof systems in the sense of cut elimination studied for Gödel-Dummett logic makes use of hypersequence, and cut freeness is a nice property in that setting. Okay, so just to wrap up, this is my last slide. Synthetic inference rules, they come from this notion of polarization and focusing. Bipoles are what we're focused on. They give rise to inference rules that only deal with atoms. Atoms may need to be in the bottom, and they may be inserted on top. But if you're only interested in bipoles, then you don't need logical connectives. That's sort of the lesson here. But you have a lot of choices on how a formula becomes an inference rule. So that's governed by this discipline of polarization and focusing. And there's these two kinds of extremes, sort of forward chaining and backward chaining, that interleave in lots of these constructions. And there's a direct proof of cut elimination for the proof systems that arise by incorporating such inference rules. And it works in both classical and intuitionistic logic. Okay, thank you.